Okay, hi all, we're team number 17, and I'm presenter Gonan. Our topic is Deep Learning Framework for Predicting Intelligence with Multimodal Neuroimage as Networks. These are four methods that we use to predict intelligence. Intelligence explains much of human behavior and cognition. Further, low intelligence in childhood is associated with mental disorder. Therefore, it is crucial to predict young's intelligence. There are two types of intelligence, and we used total cognition composite, which is basically combining two intelligence. We used ABCD dataset, which is open brain cognitive dataset for children in a raw form. And also we used NIH toolbox, which is measurement tools for intelligence. First, we performed baseline experiment by ourselves because there's not that many experiments. So we made tabular data by using mean beta weight and concatenate. TabNet is the state-of-the-art model for the complex tabular classification or regression task. Here are the results. Multimodality showed slightly better performance. However, compared to the added information, performance increase was too small. And this is because that tabular form is not really reflecting the brain's natural state. Visualization was also conducted to understand the general structure of the brain as networks. We used location of the DTI axis as node information and correlation between each node as edge information. And here are the results. We found that there are more connections through the brain in the lower intelligence brain, and it is consistent with prior studies. We also tried Graphormer to preserve graphical character of brain. And Graphormer is basically a transformer that can be used in graph. And it was possible by using 3 more encodings. As you can see from graphs, we were not really able to overcome the overfitting problem. And Graphormer is more easily trapped in overfitting problem. On top of that, brain data is also tend to overfit. So those two were not exactly the best combination. So finally, we find the graph-to-vec model. Graph-to-vec is a method that projects graph to the embedding space as a vector. Here are 3 models that we proposed. First, we made 2 graphical data. First, structured graph data is made by integrating DTI as edge volume and SMRI as node. And functional graph data is made by RSFMRI and SMRI. So our novelty was that we integrated multimodality in the data making process by setting threshold for edge volume. And then we put those 2 graphs in graph-to-vec model and get some vectors in embedding space. Since we experienced overfitting problem previously, we chose the simplest MLP model to predict intelligence. And figure 7 shows prediction by each structure graph and functional graph data. Figure 8 is showing concatenating 2 graphical data in embedding space, and figure 9 shows transfer learning. Here are the results. Unlike the Graphormer, model learns properly. And in the graph-to-vec model, the RMSE got smaller overall compared to the baseline model. This is because the model was trained while maintaining the properties of the networks, and model used 2 modalities by integrating in data making process. However, contrary to our expectation, the method of simply concatenating 2 vectors in the embedding space or transfer learning showed a decreased performance. And we conclude that it is hard to learn interaction between just 2 different modalities by those 2 simple methods. To conclude, since brain data is especially known for being noise, we needed to take care of using multimodality to get only extra information, but not noise. However, we successfully overcome that by using 2 different modalities, one as node feature and one other as edge in our graph. And here are the reference. Thank you for listening.
Okay, thanks for the presentation. Any question? Yes, Hoin?
I'm curious about the graph to back. There you used subgraph as a token of the Graphormer, and I'm curious about how can you extract the subgraph feature from the original graph.
Our response because the graph to back is implementing some very simple graph. So we just extracted the add feature as the threshold 0.2, and we just get rid of the add feature which is lower than the 0.2, and the add feature is the node feature is the they just contains only one feature, so we just added the not cortical thickness, we just added volume. So we just made a very simple graph.
So you mean you just cut the edges of the original graph?
Yeah, right. We just cut off the edges according to the threshold.
Okay, thank you.
Yeah, thank you.
We have one more question. Junbom, can you do it quickly?
Yeah. As I see, there is some overfitting in Graphormers, I think. So, do you have any solution for the problem, or your plan to overcome the weakness of the model?
So our major problem is small size of data that we use almost 2,000 grains, while Graphormer also use 400,000 local data. So we had used subset of restricted fMRI data because the subject had movements is now recursed out in our data. And I tried to pre-process, but our server is down, so everything's gone. Thus, we just drew up some high outlier data. So we just used the only 2,000 subject among almost 9,800 subjects. So if you do resting state fMRI qualification, we can use the almost the 9,800 grain. And also we have another dataset named UK Biobank, which contains 14,000 grains. Then we might avoid overfitting problem, I think.
Yeah. Okay, thank you.
Thank you.
Okay, thanks for the presentation and the questions.